Harry, welcome to the Astroben podcast. How are you?
I'm well, thanks. Nice to have. Sorry, why did I say nice to have you? Sorry. Oh
and the
God.
guest and the guest has become the host.
I know. I'm really sorry. Okay. Yes, it's nice to be here. Thanks, Ben.
Hilarious. Well, I think we're both in good spirits because we're it's getting nearer to Christmas. I mean, I don't know about you, but I'm kind of in Christmas mode at the moment as we sit here on the 19th of December. Would you agree? Are you in the holiday spirit? I would say for our American.
I'm in the sort of like festive panic mode at the moment. I think because I'm going away on quite a long trip in the new year, so I'm desperately trying to get everything done before I go. So I think it's going to be a bit of a stressful Christmas. But come the 27th, then I'll be able to relax.
Amazing. Well, let's start with that. Where are you? Long trip. Where are you going? Are you going to the moon or somewhere? Or
No, I'm off to South America for a month in January, which is the longest holiday I've had for a decade, I think. So I'm really excited about that. But really looking forward to going up to the Atacama Desert actually and seeing some of the radio telescopes up there.
fantastic. So it's you're in a unique position where you can kind of holiday sort of work and play sort of merge into each other. So you can travel the world and you're still working.
Yeah, well, writing books, that's one of the great things because you can kind of, if you're writing a book, you can email people and say, "Oh, can I come and see your observatory on a mountaintop or your particle physics lab?" And they usually say yes. And it's a great way of actually getting around and having a sort of really interesting trip where you do a bit of sightseeing, but also, you're sort of working in inverted commas and collecting material for your next project. So yeah, I feel very lucky to be able to do that.
Yeah, that's so cool. Well, look, let's start with your book because that's how I first came about yourself. Because I know you've got a book out, which is really cool, called Space Oddities. So let's start with that. Let's touch on that. So, what mysteries are there in Space Oddities? What was the motivation to write the book, and what does it aim to achieve?
Yeah, well, the book's really all about what we call in science anomalies. So sort of weird results that have been detected either in physics experiments or in astronomy that don't really fit with our established picture of the world. And this is kind of in my own, so I'm a particle physicist. I work at the Large Hadron Collider at CERN. That's my day job. And most of my research in the last, I don't know, I suppose 6-7 years has been focused on these sorts of anomalies, which could be clues to something altogether new. Because in cosmology and particle physics, there are these big unsolved questions. Like we don't know what 95% of the universe is made from, for example. There's this stuff called dark energy, dark matter, which are really just words to cover our ignorance. We have no idea what these substances are. We've been searching for decades now for clues as to, what these things might be. And there are other questions as well. And these anomalies are one of the most promising ways we have of finding the clue that kind of takes us beyond our current understanding to whatever might come next. So the book is really about, it looks at 5 big anomalies that have been occupying physicists and cosmologists in the last few years. So, the thing with anomalies is that sometimes they can be, an experimental mistake or something you've not understood in your theory, or sometimes they're this kind of key that leads you to a whole new a new window on the universe, effectively, to mix metaphors. So there's these five big anomalies that I discuss, and the thing that's interesting about them is it's not really clear yet which one of them will sort of turn into something and which ones will sort of fade away as we take more data. But there's certainly at least a couple of them that look really promising. It could be the next clue to what comes next.
Can you share a specific anomaly from the book that you find particularly intriguing or challenging?
Yeah, so I suppose, given this isn't a space podcast, the big one at the very end of the book is this anomaly called the Hubble Tension, which is really it's a problem to do with the expansion of space itself. So the standard sort of story of cosmology is that 13.8 billion years ago, you have the Big Bang, space expands very rapidly, and then it gradually sort of slows down throughout cosmic history. And one of the sort of main objectives of modern cosmology is to measure this expansion rate, because if you can measure how fast space is expanding, that tells you about the contents of the universe, the history of the universe, what the future of the universe is as well. And broadly speaking, there are sort of 2 ways to do this. One is to look at objects that we can see in the night sky, so stars, galaxies, and there are various techniques you can use to measure how far away, say, a galaxy is, and also its speed. And if you do that, you can then measure the sort of speed of galaxies as a function of distance from the Earth. And what you'll see is as you move further and further away from the Earth, galaxies appear to be moving away faster and faster from us. And the reason for that is that space itself, the sort of the fabric of space, is actually getting bigger. So something that is twice as far away from us generally will move away from us twice as fast because there's more space in between us and that galaxy, and that space is growing. So anyway, you can measure this expansion. It's what's called sort of local measurements by looking at galaxies that we can see in the sky. There's another way of doing it though, which is to look at the light that was left over from the Big Bang, something called the cosmic microwave background. And this is the sort of the oldest light in the universe. It's effectively, you know, if you look as far as you can out into space, what you eventually see is this sort of fireball of the Big Bang in the form of this very low energy microwave radiation that's been hanging around for the whole history of the universe. And if you measure that light and the patterns in that light, you can infer the properties of a very early universe. So the universe as it was a few 100,000 years after it was born. So really right back at the beginning. And then you can use our current theory of cosmology to essentially run the clock forward. So you say, okay, I know what the universe was like at the beginning. I run the clock forward. I figure out how fast it ought to be expanding today. And if you compare that way of measuring the expansion with the one looking at galaxies and stars, they don't agree with each other. So the local one comes out about 10% bigger. And this, you know, they should match up. So the fact they don't is perhaps telling us something about the contents of the universe or the history of the universe. In other words, that we don't really understand the history of the universe completely. And there may be other ingredients that shaped the universe in its early history that we haven't yet discovered. So it's potentially really very exciting. And there's been this like big area of controversy with different cosmologists and astronomers arguing over this for the last few years. But as they've like taken more data and refined their experiments, the problem has got worse and worse and worse. So it really looks like this could be the clue to something quite big.
Well, I've never heard of the Hubble tension. So does that indicate a need for a paradigm shift in our understanding of cosmology, or is it a puzzle waiting to be solved with existing framework? Because I hear a lot about, I don't know, maybe it's just scrolling on social media, but you hear sort of these clickbait articles that say, you know, the Big Bang theory needs to be rewritten. Is there a huge shift that's coming in our understanding of the universe? And do you think the Hubble tension can indicate that in some way?
Well, I think it's probably not like a wholesale revolution. It's not going to be like throw out the Big Bang theory completely, because that theory works really well. It describes so many different observations of the world around us. So it's sort of correct in some sense. But what it might be telling us is that there is some essential piece of this picture that we're currently missing. I mean, for example, so like in the standard, what's called the standard model of cosmology, which is essentially the theory of the universe as it exists. There are two big ingredients in that standard model. There's dark energy, which is this kind of repulsive anti-gravitational force that's making the universe get bigger, faster and faster. It was kind of the first evidence for that was discovered back in the late 90s. And there's something called dark matter, which is an additional form of invisible matter that adds extra gravity to the universe, holds galaxies together and various other things. Now, these are the two main ingredients in this theory, but we don't know what they are. So you have this theory that sort of relies on two completely unknown substances. So in some ways, it's not surprising that this theory doesn't necessarily line up completely with what we observe, because we really don't understand a huge amount of what ultimately goes into it. In terms of what it could be telling us, there are a load of different theoretical explanations. The classic thing with anomalies is if there's one anomaly, you'll get 100 theory explanations for what might be causing it. One possibility, the most popular, is this idea of something called early dark energy. So this is a form of repulsive energy that would have existed in the universe very early. So sort of during the first few 100,000 years, when the whole universe was this burning fireball, essentially just after the Big Bang. And then this early dark energy sort of switched off or sort of faded away as the universe aged and expanded further. So that is one possible explanation. It doesn't, the there's other ones that involve, revising our theory of gravity, or introducing new types of interactions between different fundamental particles in the very early universe. So the honest answer is we don't really know. And I think one of the things that for a long time made cosmologists doubt that this effect was real was that there was no really compelling theoretical explanation for it. It was very hard to come up with one idea that just solved the problem. So the honest answer is we don't really know, but it seems like it's telling us something really quite profound and fundamental about the universe. And that, if we discover there's a new form of energy, for example, out there in the universe, or some new force between fundamental particles, that would be a really big deal and have knock-on effects in our understanding of, not just cosmology, but also particle physics and fundamental physics.
Fascinating. Well, although you do have a book out, your main day job is as a researcher at CERN. And so you've been at the forefront of particle physics debates. Well, not necessarily debates, but I'm sure, the research in itself is trying to answer these big questions. Are there any ongoing discussions in the fields that you find particularly exciting or contentious about the work at CERN? And what, as we're coming to the end of 2023, are there any particular experiments that CERN is looking to do in 2024 that you could speak to?
Yeah, I mean, so I started out in particle physics just when the Large Hadron Collider switched on. So the LHC is this giant 27-kilometer circumference particle accelerator. It's the biggest scientific instrument that's ever been built. I think by some measures, it's the biggest machine. So I came in as a sort of young graduate student just as it was switching on. And so that was back in 2010. And back then there was a lot of excitement about what the LHC might find. And there were sort of two big goals, basically. One was to discover something called the Higgs boson, which you may have heard of, which is sometimes in the popular cultures referred to as the God particle, which isn't a name that physicists like very much, but that basically represents the fact that it was really, really important to find this thing, which is in some sense the last missing piece of our current theory of particle physics. But then the big objective was to try and find signs of new fundamental particles. So something that might explain what dark matter is, for example. And the last 10 years, really, the experiments have worked beautifully. So you have this incredibly complicated international project. The accelerators, run beautifully. The experiments have run beautifully. But what we've actually discovered is that none of the things that were predicted beyond the standard model have been found. So we haven't found dark matter. We haven't found micro black holes. We haven't found a lot of the other exotic things that were hypothesized, more than a decade ago. So physics is in this sort of slightly strange place now where we have these really big unanswered, unsolved mysteries, the nature of dark matter. Another big problem in particle physics is the fact that we exist at all. Our current best theory basically says that all of the matter that we're made of should have been annihilated in a reaction with something called antimatter just after the Big Bang. So about a millionth of a second after the Big Bang, it should have been game over. That should have been the end of the universe. And so the fact we're here is a big theoretical puzzle as well. So there are lots of reasons for thinking there must be new things out there, new forces, new particles that can explain some of these mysteries. But so far, nature has been really cruel to us and basically said, well, I don't care very much for all your clever theoretical ideas. So we haven't really got much of a clue. And this is why these anomalies have become so important. So in my experiment at the LHC, we study a particular type of fundamental particle called a bottom quark, or sometimes called a beauty quark, which is a fundamental matter particle. It's akin to the stuff that makes up the nucleus of ordinary atoms, but kind of heavier, more exotic. And what we do is we measure how we produce lots of these things in the collision. You get billions and billions of them made every year. And the game we play is to study their properties really precisely and compare that to the predictions of our theory. And the reason you do this is these bottom quarks are very sensitive to the existence of new forces, for example. So if there's a new fundamental force in the universe, it can affect how these particles behave. And in the last few years, we've seen evidence that they are indeed behaving in ways that our current theory can't explain. So it's become a really hot topic, also an area of quite a lot of controversy, because when you see these sorts of anomalies, you never really know, am I really seeing something fundamentally new? Or is it the fact that I've misunderstood something about how my experiment works? Because these, I don't know if you've ever seen pictures of these things, but these detectors that we use, they're like the size of cathedrals. They're these enormous, incredibly complicated instruments. And understanding how they work and how they detect particles is actually incredibly complicated. You have to take all of that into account when you're making your measurement. So there's always a chance that you've made a mistake experimentally, or maybe that we've miscalculated using our current theory how these things should behave. But the sort of third possibility is that we are really seeing something interesting and new. So that is sort of where a lot of the focus has been in the last few years. And we're in this rather frustrating position at the moment of not having enough data to really be sure that what we're seeing is real. So what's coming in the next few years is the LHC is going to undergo a major upgrade in the sort of latter part of this decade, which will basically increase the rate it can collect data. So how many collisions per second you get effectively, because the more collisions per second, the more data, the more precise your measurements become. So the idea is to basically increase the rate we can take data by an order of magnitude, more or less. And that will allow us to accumulate so much data that we can really hone in on these anomalies and figure out whether they're the real deal. So we have to wait a few years to get a final answer in all probability.
Wow. Do you think the physics community globally is doing enough to put the investment, not that it's the physicists putting in the investment, but to try and answer these big questions? You need to build big machines and big experiments, huge infrastructure, as you say, the biggest man-made experiments, human built, imaginable. Do you think there's a sort of lack of will from governments and private companies to fund these big projects? Because the Large Hadron Collider is fantastic, obviously, but does there need to be 10 of them globally pushing the boundaries and pushing the envelope to answer these questions? Does there need to be one in space? Do you think there's do you think there needs to be a real, well, I guess, just global investment and focus on this if we're going to get the answers?
Yeah, so at the moment, one of the projects I'm involved in is CERN are currently thinking about what comes after the LHC. So the LHC will run until the mid sort of 2040s, and after that point, it will shut down. And the question is, what comes next? And what a lot of my colleagues would like to do is build another collider, but an even bigger one. So we're talking something on the sort of 90-kilometer scale, so 3 times bigger, 10 times more powerful. And these projects, obviously, they come with really big price tags. So you're talking tens of billions to build these things, and over many, many years. The moment, what we're trying to do is develop the science case, so the scientific arguments for why you want to do this, and sort of looking at all the technical challenges and so on. So I suppose one of the frustrations, I guess, of being in high energy physics is that you do work on these incredibly long timescale projects. And it's not so much a case. Actually, in a way, high energy physics has been quite good at attracting large investments from governments over a long period of time. So, for example, being a member of CERN is the international organization that hosts the LHC, and it's a broadly European scientific body, but it actually has members, including the United States contributes, historically Russia and China contribute as well. And other countries around the world. So it's really now a kind of global particle physics lab. And there's a certain amount of scientific prestige associated with being part of this club, effectively. So it's actually been governments, there has been cases in the past where, say, countries have thought, well, I'm going to cut my funding to CERN or pull out. And actually, they found it very difficult to do that because it's sort of essentially admitting that you're no longer a first-rate scientific nation if you don't want to sort of be part of this big scientific research program. So in some sense, we've actually been quite successful in attracting funding, because one of the problems is, like, if you're planning a project that takes 30 years, funding needs to be stable over that period, and governments aren't generally that good at making long-term investments. They kind of work on election cycles. So the fact that this actually has happened and has been successful for such a long time is kind of a quite impressive achievement, I think. In terms of, do we need more money? We do spend a pretty paltry sum on research and development. Particularly in this country, our research budget is much lower than it is, say, in Germany. We could certainly be spending a lot more. But in terms of these sort of experiments, it's not necessarily we would need several of these colliders. There is a possibility that you might get one in Europe. Chinese may decide to build one. The Americans have their own set of priorities where they're building different types of experiments. Really, what you want is a diversity of projects. So you want big projects that will kind of run for decades, but you also want smaller experiments that look for things that are maybe a bit more niche, because you never really know where the next discovery is going to come from. So you need a broad program to make sure that you can kind of capture all the possibilities. And that's really what we're sort of working towards. It's not just a massive super scale project. It's also the more modest things that are done on a budget of a few million, not billions.
No, sure. No, it's no joke that it's even going. And speaking of jokes, I wanted to chat to you about a former life. Well, I assume it's still former, but tell me about your experience as a former stand-up comedian. Because just listening to you talk, like you're very engaging, and maybe it's because we're both English that I don't need to think too much about what you're saying, just because of we have the same accent. But you're very good at communicating and breaking things down to idiots like me that don't really understand the complexities of the science. Bottom quarks. Do you think that experience? Well, tell me about your experience as a stand-up comedian, actually, and how has that sort of affected your science communication and how you creatively apply yourself to particle physics?
Yeah, I mean, the way it came about, it's more than 10 years ago now, but there used to be this thing run by University College London called Bright Club, which was a really kind of neat idea. Essentially, they identified this problem, which was that science communication broadly reaches two groups, which was sort of kids at schools. There's a lot of educational outreach that goes on from universities and science departments and so on. And then after that, nothing really happens until people get into their sort of later middle age and retirement, where they start watching documentaries or listening to Radio 4 programs. And they identified this problem that people in their 20s and 30s weren't really engaging with science. The idea was to do something that was really targeted at that sort of demographic, basically. And so they set up this stand-up comedy club, which was called Bright Club. And the idea of it was it was in a comedy club or a pub somewhere. I think the first ones were in Clerkenwell in sort of North London, Central London. And you'd have a professional comedian. They have quite often quite big names, like Robin Ince would say host the evening. And then you'd have 8 stand-up acts who are all academics. I think it started off as just scientists, but then it became actually pretty much anything. So you might be a professor of, ancient Egyptian history. You come up and do 8 minutes on the pharaohs or something. So at the time I was just finishing my PhD in Cambridge, and they set up a Cambridge branch and put out a call for people to take part. So I signed up. I think I was kind of feeling a bit demob happy as I was almost at the end of writing my thesis, and this will be a bit of fun. I mean, I have to say though, it was the single most frightening thing I think I've ever done, because back then as well, I didn't have quite so much experience sort of talking to the public, but also there's something extremely binary about doing comedy, because if you get up there and you're not funny, it's very obvious, no one's laughing. Whereas you can give a talk and you can get a guess how maybe people are sort of look like they're paying attention or not, but it's not so, obvious that you're really bombing. So, and the thing about comedy is it's so much, normally when I give a talk, I don't prepare what I'm going to say. I have a sort of sense of what I'm going to say, but I don't prepare it word for word. Whereas comedy so much moves on, exactly the intonation you use when you say something, or the timing or the pauses, that you really have to know what you're going to, well, at least I did. I sort of really rehearsed this 8-minute set down to every sort of word and timing and every upward inflection. So there's a real fear, because when you've memorized something like that, if you lose your place, you're really screwed, basically.
Yeah.
But anyway, so I did it, and it was absolutely terrifying. But it went actually really well, and then I got invited to do it a few more times in London. So I think saying I was a former stand-up comedian is probably putting it a bit strongly, but I certainly did. I think I did a sort of half a dozen stand-up comedy performances back when I was in my mid to late 20s.
It's brilliant, and actually, I speak to a lot of. I've had a lot of science communicators on the podcast as well, and always been thinking about how to engage with young people, because you're exactly right. There is definitely a sort of pipeline where the interest in space as well as science sort of peters off. A lot of kids want to be astronauts, and then that peters right off as go through the school system, etc. And it sounds like a great idea. I don't know if it's still going, but I
don't think it is in its form, but I think it's science and comedy is still a really strong vein. I think because because science is seen as so intimidating, it has this reputation for being hard and difficult and inaccessible. I think that it's actually marrying it with comedy is a great way of sort of breaking down. Like, when you make someone laugh, you're immediately connecting with them, and I think that's why it's become if you think about Infinite Monkey Cage, Robin Ince doing a lot of sort of science-based comedy, Dara Breen, people like that. It's quite a strong vein in sort of television and radio, and I think that in some ways that sort of began actually back with Bright Club. They were one of the pioneers of that. So it's it's a great thing they started. It's a shame I don't think it is going on, but it spawned lots of other things subsequently.
Yeah, no, Dara Breen's a great example, and actually, you think of science communicators like Bill Nye and Neil deGrasse Tyson, Brian Cox. What they all have is they're just very captivating speakers. And if I think back to I didn't have the best teachers at school, but I imagine the best teachers and professors. They're getting up every day to talk for hours. So you do, there is definitely a synergy between teaching and stand-up comedy. It's that kind of being able to talk on your feet for hours and having the frameworks, and if you do lose your place, being able to get back to what you're talking about. So that's no easy feat. I'd like to see more of it. I'd love to see more physicists and space leaders, because even space, something as exciting as the space industry, we don't have a lot of people, not just in the UK, but globally. There needs to be, especially as the Artemis programs, we go back to the moon, onto Mars. There needs to be a real kind of, comedians talking about space, musicians talking about space, influencers, rappers. Like they all need to be sort of bringing it into their culture.
Yeah.
Well, look, it's been great to chat to you. I've got a few quick fire questions, if that's okay.
Oh yeah, sure.
Some of them I've just written down just now. Some of them are one or the other. Others you might want to give a bit more detail on. Black holes or neutron stars? That's the question.
Oh, black holes, I think. Just because...
Why?
Well, because I think black holes are where a lot of the really gnarly problems in fundamental physics lie. And like so many people spend their time studying black holes because that's how we're going to learn about quantum gravity, possibly even the beginning of the universe. So I'd probably go for black holes. Neutron stars are very cool as well, though, unquestionably.
If you could travel to any planet in our solar system, where would you go first and why?
Ooh. Can I choose a moon? Is that allowed?
Definitely.
Can I go to
celestial body?
I think I go to Europa. I think the moon of Jupiter, and drill under the ice and see what's in the liquid water ocean. If there's any sort of microbes or maybe even Jovian fishies swimming around.
Well, actually, this week hasn't there been something that's come out about that? That there's again, it might have just been the headline that I read without actually reading the article. But has there been any recent discoveries on that?
Not that I've seen, but I've been slightly unplugged from news the last few days, so I don't know what's been going on. But maybe I have to go and read the BBC website after this.
Exactly. I always ask people this, and it always puts them on the spot a bit. What's your favourite space-themed sci-fi movie or TV show?
I think if I'm being honest, I would have to say Star Wars, which is a bit of a strange choice in a way because it's not really a science fiction. It's basically Camelot with wizards in space. But I think that was one of the things that when I was a kid, I was absolutely obsessed with. And now I'm a bit more grown up, actually. When I watch Star Trek, I think, I rather like the kind of the politics of Star Trek. But at the time, I found it a bit dull, I think, when I was small. So maybe Star Trek's one for slightly more mature people. I don't know.
Again, another question, which people might roll their eyes me asking, but do you think we'll ever experience or discover extraterrestrial life in our lifetime? I know asking a physicist this is a bit like a bit cringe, but I'm kind of intrigued. I'm kind of, on the one hand, I'm really hoping we do, but even if we don't, that's a sort of thing in itself, isn't it?
I think there's a good chance we'll discover single-celled extraterrestrial life in our lifetime. If we're going to be going to Mars in the 2030s, landing more probes on the moons of Jupiter, I think there's a decent chance we'll find evidence of life on other planets. But in terms of like intelligent life, I think that's much less likely. I would say intelligent life, no, but some form of single-celled, simple life, I think there's a very good chance.
Mm. Well, look, final question, and it's sort of a bit further than the moon and Mars. Interstellar travel. You know, as a physicist, you're a lot smarter than me. Is interstellar travel? Is it, obviously it's not achievable now, but do you think there's a, you know, with you know, the rate of technology and AI and, you know, over the next couple of centuries, do you think interstellar travel will be achievable, or do you think it's sort of a forever dream? And I'm not talking about sending probes, I'm talking about humans. We might be bionic humans, but do you think there's a physics way of doing this?
In terms of shortcutting the speed of light at the moment, no, it looks like that's not possible. But, you know, I guess interstellar travel is possible if you're willing to be patient. If you're happy to go on a 1,000-year voyage, you know, with an enormous spacecraft where you spend a lot of time in hibernation, then yeah, maybe. I think that could become possible. I suppose the question is, why would you do it? Maybe you're going to get some kind of group of really committed people who decide they want to lock themselves in a giant ship and go to sleep for 10,000 years and get to Alpha Centauri. But in terms of, you know, some revolutionary technological breakthrough that gives us warp drive, I think that looks pretty unlikely. Actually, this is not a short answer, but there was a really cool experiment that was done at CERN earlier this year where they measured whether antimatter falls under gravity or whether it might be repulsed by gravity, because that no one had ever seen. If you make an anti-atom and let it go, which way does it go? No one knew. And if it had fallen upwards, that would actually have been a potential route to making warp drive a reality. But unfortunately, as everyone expected, it fell downwards. So that kind of, unfortunately, is a bit of a problem if you want to invent a warp drive type system. So it looks like we're just going to have to go slowly if we do ever go.
Fascinating. Well, look, it's been great to chat to you. I've got an e version of your book, so I'm going to read it over Christmas. And yeah, I'd love chatting to you. I think your sort of witty your witty style definitely comes over, you know, just chatting, and you know, something like Space Oddities. You know, no one has all the answers, but you know, you've got to sort of be fun with these big questions. I think you know, be humble, but also you know, smile about it and laugh about it, which I think we do in the UK quite well. But yeah, thank you so much, Harry, and
thanks,
hopefully
mate.
speak to you again soon.
Likewise. Have a great Christmas.